Alright, welcome back. So let's look at a more interesting version of this echo program, this hello world. Let's throw in some more channels and do some simple calculations just to get an idea for what the language can do. So um, let me start my analog I/O system again. We'll put that in the background. And let's look at a new file, echo1.txt. So echo1.txt does the following. It takes what comes in from the left side of cell 00 and it just sends it right out to the left side again. So that's our straight echo again. It also takes what comes in on cell 00 from the left side and it sends it to the right. So it's sending the incoming value from the left to the cell on the right, the cell in column 1. And the cell in row 0, column 1 is taking the left value that's coming in. So that's the value coming from cell 00, subtracting from 63 and sending that out to the K side, which is physically on the top of the cell matrix, the top edge. So what do we have here? We have an incoming signal to cell 00. We have that being echoed back to the left, and we have 63 minus that value coming out of the top of cell 01. Okay, 63 is a magic number because internally all the values go from 0 to 63 because everything's digitized with 6 bits. So if we look at the configuration of echo1, echo1.config, we see that channel 0 is going to go, channel 1 is going to go into the main input. The echo is going to come out on channel 0. The complemented echo, the K from cell 01, is going to come out on channel 1. And channel 2 is coming from cell 00's control left output. So this last line is saying if the incoming value is bigger than 31, set the TT of 00 control left to 12, otherwise set the TT of 00's control left to 48. So we've got a bit of a clipping function here. If the input coming in is below the 50% range, it'll set the C output to 12. Otherwise, it'll set the C output to 48, so it sets it to 25 or 75% of full value. And the two things to note in here, one, in this statement up here, we're doing some arithmetic on the value we're sending to K. We're doing 63 minus alval. That's not too bizarre. The more interesting thing is down here, we have an if statement, and it almost looks like we're doing conditional compilation here at runtime. Because if the L value is bigger than 31, the truth table of the cell is somehow going to do this, send a 12 to CL, otherwise it's going to send a 48 to CL. But this behavior gets statically encoded inside the compiled bin file. So what's happening is it's basically storing the function. So it uses this C statement, and when we compile it, it basically analyzes this and figures out what configuration information to store inside the cell in order to achieve this behavior, to mimic this behavior. So this is not actually executed at runtime, right? When the system's running, there's no C code inside. There's just embedded functions, but the function that's embedded will cause this behavior to happen. All right, and that C output, again, will simply go to channel 2. So let's compile this, compile echo1, and that compiles fine. And now let's run it. So engine-echo1, and it reminds us what our inputs and outputs are. And if we come over here, input channel 1 should drive the whole thing. So channel 1 goes directly to channel 0. As you can see, channel 0 is mimicking it. The complement of channel 1 is going to channel 1. So these two should always add up to 5 volts, right? Channel 1 is just showing the opposite of our input. Channel 0 is tracking our input. And channel 2 is either 3/4 of the full value if our input is low, or 1/4 of the full value if our input is high. So small inputs, it sits at 3.8 volts, should be 3.75 if it wasn't rounded, and 0.9 some volts if the input is high. Again, these are sync messages that will come out periodically. You don't have to pay attention to those. So let's exit this and let's take a look at, oh, I exited instead of hitting attention. So just Control C. So let's take a look at echo1.txt again. So if the input value is large, it sets the C output small, otherwise the C output goes high. So that's the behavior we were seeing. So let's run this one more time, analog IO, and redo our engine code. And the output on channel 2 is either small or high. The output on channel 1 is the opposite, and the output on channel 0 is the true value. Alright, so that's the basic behavior of the system. That's a more complex program, but it's still basically a hello world kind of behavior. So the next video we're going to look at some much more interesting behavior. We're going to implement a D flip-flop, but it's an analog D flip-flop, so it's basically like a sample and hold. And there's another video posted that goes through the description of the circuit and how the circuit does what it does. So in this video I want to actually look at the source code, compile it, run it, and see how it behaves.